Okay, this third session is going to discuss the rationalization of wave-particle duality. We're going to take a moment to consider what we mean by wave-particle duality and how we pull it together into some idea that makes a little bit more sense than this situation we seem to have, which is that we have a wave model and a particle model and they don't mix. As we saw in the last session, sometimes light seems to behave as a set of waves, and if it's behaving like that, using the particle model ends up messing things up. We cannot explain the observations that we see. Examples of this are reflection, refraction, interference and diffraction, the so-called wave effects. At other times, light seems to behave as if it's a collection of particles. And if we use the wave model, that gets messed up, doesn't explain the observations. Examples, the photoelectric effect, emission and absorption spectra. Okay, before we get into it, let's just briefly review what we said before with respect to wave-particle duality. Louis de Broglie, as part of his PhD thesis, made a comment about the existing understanding of physics at the time, and then went on to make a new statement that at the time very few people believed. His statement about the existing point in physics was, electromagnetic radiation shows wave-particle duality. His new statement was, matter also shows wave-particle duality. And he made 4 statements that we're particularly interested in. He stated that matter can be described as having a wave nature. The wave that we write down is called the wave function. The square of the wave function is proportional to the probability of finding or locating the particle. And finally, the wavelength, lambda, is given by Planck's constant divided by the momentum of the object, mv. Okay, so the rationalization of wave-particle duality. What does this actually mean? Let's try and pull this idea together so that we can make a little bit more sense of it. Feynman and others worked on pulling these 2 ideas together and imagined that we could consider electromagnetic energy in the following way. First of all, as a wave. This was the standard model that was basically used at the time to describe light. Also, we have the particle model. Now, the particle model of light has this idea that we have what's called a photon, a tiny lump of electromagnetic energy traveling at the speed of light. Now, these 2 ideas can be pulled together, and Feynman and others pulled them together by imagining, rather than having this infinitely oscillating wave or a tiny particle, we have the following. Imagine that a piece of electromagnetic radiation has a shape which is basically 0 and then starts to build up in amplitude, reaches a peak of amplitude and then dies away, going back to 0. And this would be a pulse which would travel at the speed of light. You could imagine quite easily that this could be created on, let's say, a slinky. You get a slinky stretched across the lab, one person holding one end, one person holding the other, and one of them oscillates their hand 3 or 4 times and generates a pulse which travels across the slinky. This has the advantage of having a significant amplitude and effect over a tiny region of space, or in this case the slinky, like a particle. But clearly within the particle it has a wave nature. Now, this model was referred to as QED, quantum electrodynamics. And quantum electrodynamics is incredibly mathematical, but in all of the situations where it's been applied, it has always been able to give us the right answer. So, what do we mean then by probability waves? De Broglie said that the wave associated with an object is a probability wave. It doesn't mean that, for example, a person is a wave. It doesn't mean that, for example, when a person walks through a door, this would be like a wave moving through a gap and spreading out, diffraction. It doesn't mean that a person would walk through a door and suddenly they become more chubby as they spread out physically. The concept of the probability wave is really linked to the idea of a confined particle. Now, in physics, the concept of confinement is incredibly important, and the word confinement means exactly what you think it means. If something is confined, it means that it's restricted to a particular region of space. So, for example, imagine the room that you're in right now. All of the particles in that room, in let's say the air around you, the oxygen, the nitrogen molecules, etc., they're all confined to the room. The idea is that a confined particle is restricted to a particular region of space. So, let's consider a real example. Around you will be some oxygen. So let's consider an oxygen molecule in a room. And we'll just consider, for simplicity, one-dimensional motion. So imagine that an oxygen molecule is in the room and it is bouncing between one side of the room and another. Let's not worry about the fact that the oxygen molecule might bounce off other oxygen molecules and nitrogen molecules and argon, etc., etc. Let's just consider, to keep things simple, the idea that we have an oxygen molecule bouncing backwards and forwards. It hits a wall, bounces off the wall, goes across the room, hits the wall, bounces back, and then hits the original wall again. Just keeps doing that. Now, confinement means that as the particle hits the wall, it cannot enter the wall. In this way, the oxygen molecule is a confined particle. Now, this means that whatever wave or wave function we care to draw to represent the oxygen molecule, it has to have a property at the confining edges where it has to bounce back. The wave has to be zero. If you like, the particle cannot enter the wall, so one atom into the wall, whatever wave function we draw, it has to be zero there. If it wasn't zero there, then according to De Broglie, when we square the shape, we'll end up with a non-zero value inside the wall. And that means the particle can be inside the wall, and that means the wall is not a confining barrier. The only way that we can have zero probability of the particle being inside the wall, just one atom deep, that's all, is to make sure that whatever wave we draw, it has zero at the edges. And that would look something like this. And here we've drawn three possible waves that have zero at the edges. The shaded edges are representing the walls. The blue curve starts at zero, ends at zero, rises in the middle. The green one rises, falls down and comes back up again. And the red one has got three of these kind of half wavelengths. For those that understand and have already carried out work on standing waves, they'll recognize the fact that effectively we're drawing something alike to standing waves on a guitar string. Now, let's consider these waves individually. The blue one, we're looking at the wave function there. Now, De Broglie said that if we square the shape of the wave, we will get the probability function, a function which tells us the probability of locating the particle. So in the blue wave, if we square that shape, it kind of looks the same. Starts at zeros, goes up to a peak in the middle. This is telling us that if the oxygen molecule is represented by the blue wave, then it is most likely to be found in the middle, where the probability will be highest. If we then look at the green and the red, we get slightly different probability functions, as shown here. So the blue one, as we said, has a probability function that has a peak in the middle. If we could stop time and look at where the particle was, stop time and ask where is the oxygen molecule, then restart time and then stop time again, look at where the oxygen molecule is. Keep stopping time and starting time and stopping time and basically mapping out at random times where the oxygen molecule would be. It would produce a shape that looks like the probability function. It is most likely to be found in the middle. Okay, the green wave function. If the green wave function is representing the oxygen molecule, and note again it has zeros at the ends, that's required if the walls are to be confining, then when we square that shape, we get two of these bulges in probability. This would tell us that if we could do this kind of imaginary experiment of starting and stopping time and looking at where the particle is, we would find that the particle is most likely to be found in the middle of one half of the room, or equally probable that it will be found in the middle of the other half. And what's particularly interesting is it would never be found in the middle, like it isn't found at the edges. Now this is really weird. Finally, with the red one, we have three of these probability lobes. Now, since we're assuming that the particle does exist, then obviously the integral, or the area under these probability functions, needs to add up to 1. The important thing to note about these probability functions is that not any function is allowed. Only wavelengths that have zeros at the ends are allowed to be drawn, are allowed to be considered. If we were talking about standing waves, we'd be saying that the end conditions have to be a node and a node. Now, this diagram only shows the first three. Of course, in reality, there would be an infinite number. The blue one has 1 half wavelength between the walls. The green one has 2 half wavelengths, which of course, as you can see, is a whole wavelength. The red one has 3, and there'd be 4 and 5 and 6, etc., etc. Okay, let's consider the first probability function that we've drawn here. Consider an oxygen molecule described by a probability function like this. Where the 0 starts and the 0 ends, that's basically the physical size of the room, or it's representing the physical size of the room, and the probability has a maximum in the middle, falling to 0. Now, this may not seem too outrageous a function, but let's just look at it and think about it in a little bit more detail. Oxygen at room temperature behaves like an ideal gas. So let's just recall something associated with an ideal gas. Ideal gases are gases that have no potential energies associated with them. We're going to ignore the issue that the oxygen molecule has a covalent bond and that we could actually store potential energy inside that. We're only interested in imagining the oxygen molecule behaving like a particle. No potential energies. Which means as the oxygen molecule bounces across the room from the one side to the other, there are no forces acting on the oxygen molecule except at the points where it hits the wall and bounces off them and changes direction. Clearly, it accelerates when it hits the wall because it literally changes direction. The properties of an ideal gas are summarized in what are known as the 4 assumptions of an ideal gas, and we use the word AVET written here to try and remember them. Just briefly, E stands for elastic collisions. A stands for attractions are negligible between the gas particles and other gas particles and the walls. V is the volume. The volume of the gas particles themselves is negligible compared to the volume occupied by the gas. And finally, T. The time of a collision is negligible compared to the time between collisions. In other words, the particles spend most of their time not colliding, not in close proximity to other particles, but travelling around without any influence whatsoever. Now, since the particle will oscillate between the walls, backwards and forwards, but it has no forces acting on it as it travels between the walls, then what this means is that it will not accelerate. The total force is zero, therefore F equals ma. There is no acceleration. So between the walls of the room, the particle will simply travel at constant speed until it hits the wall, bounces off the wall, and then travels at constant speed again. Which means that if we were to draw a probability function for a particle, in this case like an ideal gas, it is most likely to be found anywhere. Because it's travelling at constant speed, there is no particular point at which the particle is more likely to be found than any other. So this would produce a probability function that looks like this. Now that is clearly not like the probability function that we're talking about. Okay, well, is there any other situation where we could consider an object bouncing backwards and forwards, oscillating backwards and forwards? And in fact there is. There's the idea of simple harmonic motion, SHM. In SHM, a particle is moving backwards and forwards, either left and right or up and down. One of the classic systems that show simple harmonic motion is the so-called mass spring system. And that's shown here. The idea is, for example, imagine that you attached a spring to some kind of mount. It could be the ceiling as is suggested in this diagram, or it could be a clamp from a retort stand and a boson clamp. You hang the spring, you put the mass on the end of the spring, you pull it down slightly and you let go, and the thing oscillates. Now we could have this horizontally or, as it's shown here, vertically. But the point is, the thing is oscillating backwards and forwards. The extremes of its motion are the points of the two walls. Now if we do this, and you could imagine maybe the particle attached to two springs to do this, and you ask yourself, what will the probability function look like? Now the easiest way of thinking about this is to imagine what happens when something oscillates as we see here. As the mass oscillates up and down, it's moving fastest in the middle of its oscillation, and it's slowest at the ends. It obviously is stationary when it reaches its highest point and its lowest point in this vertical motion. So it shoots through the middle with its highest speed, and it slows down as it reaches the edge, stops, turns around, and starts to accelerate back inwards towards the middle. If you then ask yourself, where is it most likely to be found? Then it's most likely to be found where it's travelling slowest. This will produce a probability function similar to the one shown here. So the idea is that this produces a higher probability near the walls because that's where it's slowest. Now clearly, again, we're looking at different types of motion that could be used to describe a particle going backwards and forwards. And we have a probability function that looks like that for SHM and that for an ideal gas. And in both cases, this does not look like the probability function that de Broglie is considering. So this probability function associated with Louis de Broglie and his idea of wave-particle duality is a very unusual probability function. It does frankly not make sense. And we end up then in a situation where we run into one of the big problems of quantum physics. The idea that somehow, some way, this process does not make sense. At least not in the conventional way. Okay, we're going to stop there and basically accept the fact at this stage that this is a little bit weird, that the probability functions produced as a result of what we're referring to as confinement are slightly unusual. And we haven't even considered the idea that there could be some probability functions that have zero in the middle. That's really weird. And in the next session, we'll look in a little bit more detail at the other probability functions, what they mean for a particle, and we'll actually do some calculations to try and make some kind of sense of this. It would be nice to know whether de Broglie's idea is actually sensible somehow, or whether it's complete and utter rubbish. And frankly, if it is sensible, if there's something that's correct about de Broglie's idea, then it would be nice to try and understand why we don't see this in the real world. Why, for example, when a person walks through a doorway and they behave like a wave, they don't actually spread out or produce a diffraction pattern. So, until the next time, I hope that you found this useful, found it interesting and somewhat intriguing, and we'll continue in the next session.